Okay, so here we are. We're still looking at shear and bending and beams, and now we're going to add in fasteners. So we have a wooden beam. It's fabricated from 1 2x10 and 2 2x4 pieces of dimension lumber to form an I-beam as shown. The flanges are fastened to the web. So the flanges, let me move this up, the flanges are fastened to the web with nails that can safely transmit a force of 120 pounds in direct shear. If the beam is simply supported and carries a 1,000-pound load at the center of the 12-foot span, determine the horizontal force transferred from each flange to the web in a 12-inch long segment, the maximum spacing S along the length of the beam required for the nails, the maximum horizontal shear stress, the maximum normal stress. Okay, so when I'm looking through this, we'll get to this one kind of at the end, but right now we're going to look at maximum spacing. So we have this new equation where I have little q equals VQ over I. And little q, remember, is our shear flow, and it's the force of the fastener divided by the spacing. If I want the maximum horizontal shear stress, VQ, IT, normal stress, normal is MY over I. And all of these are maximum, so I need to come back and look at my system of where I have my maximum shear and moment. So I do have 1,000 pounds here. And again, I'm giving you the shear and moment diagrams, but understand you might have to draw these yourself. So we always start with equilibrium. And if this is 1,000 pounds, these have to be 500 pounds up, 500 pounds up. So I'm going to go up 500 units of pounds, across, down 1,000, over, and I'm over here at negative 500. I know that the area under the curve, so my entire length is 12 feet. So this is 6 feet. This is 6 feet. I know the area under the curve creates the moment, and this area is going to be 500 pounds times 6 feet. So I get 3,000 as my maximum, 3,000, and my units are pound feet. So I'm going to have to remember to convert that to inches. So my maximum shear is 500 pounds. My maximum moment is 3,000 pound-feet. It is a positive moment. So I have compression top, tension bottom. Okay. So let's go through the top then. I think that covers everything we have. So the maximum spacing S. Oh, my section property is already given. So let's start with spacing. Now the nice thing about this beam is that it is symmetric, so whatever spacing I find at the top is going to be the same spacing I find at the bottom. And it doesn't matter where I am, 500, 500, 500, 500, our shear is just 500. So the force of a nail divided by the spacing equals VQ over I. Okay, I was told that the force of my nail can carry is 120 pounds, 120 pounds. I'm trying to find spacing. My shear is given as 500 pounds. My moment of inertia is given as 748 inches to the fourth, so I need to find Q. What am I nailing onto the system? What am I nailing onto the system? I am nailing this piece of wood onto the system. Because of symmetry, I know that icentroid is symmetrically right in the middle. It is 5 inches up, 5 inches, and then here we are 2 inches up. So if I want to find that centroid, 1 inch, 1 inch, it is 6 inches up to the centroid. So when I'm looking at Q, my Q, I'm going to have the area that I'm nailing on. So I have 4 times 2. I have to walk 5 inches up plus another inch to the centroid. So now we can just rewrite this to discover our spacing. Spacing equals, okay, force of my nail, the moment of inertia, divided by VQ. So we went over there. These are coming over here. I have 120 pounds. 748 inches to the fourth, divided by V, 500 pounds, and Q. 4 times 2 is 8. 8 times 6 is 48 inches cubed. So let's calculate that out. 120 enter, 748 times 500 divided by 48 divided by, and I get a spacing of 3.74 inches. Now, usually we're not going to tell somebody that they have to nail, nails in every 3.74 inches. We're going to give them more of a rounded number. Do I want to round up to 4 or 3.75, or do I want to round down? So if we wanted them at every ½ inch on center, my spacing is going to have to be 3.5 inches. This is the maximum I can have them apart. The farther apart I make them, the higher force I need in that nail. So my spacing, whether I'm looking at the top or the bottom, and whether I'm looking on any length of my beam, my spacing has to be 3.5 inches on center. Okay, 3.5 inches on center. So now we want to go back and figure out what is our maximum horizontal shear stress. Well, our maximum shear stress is VQ over IT, and we're going to do the same type of a scenario. I have 500 pounds. My I was given as 748. My thickness, I have to remember that my maximum occurs here, okay? So my thickness here is, I believe it's a 2 by 10. My thickness is 2 inches, so now I've got to determine what is Q. So when I'm looking at Q, I can either go up and look at all of the area above, or I can go down. So we've already found Q of this piece. Okay, we've already found Q of this piece. It was 48 inches cubed. So now I can find Q of this piece and add on to it. It is 5 inches tall, which means its centroid is at 5 over 2, and it has a width of 2 inches. So our Q is going to be pretty easy this time, because it's going to be that top that we've already discovered, 48 inches cubed, plus base times height times distance to the centroid. And we get 48 enter, 10 times, 2.5 times 25, so 25 plus 48 is 73 inches cubed. So our maximum shear stress is 500 pounds times 73 inches cubed divided by 748 inches to the fourth divided by 2 inches, which is my thickness right there at that centroid. So I have 73 times 500 divided by 748 divided by 2, and I get a maximum shear stress of 24.4 psi. Okay, and now we can go back and we can do the same thing. Let's find our normal stress. Okay, because of symmetry, I know that my C to the top and my C to the bottom are the same. So if I look at this, I have this value to the top, and that's going to be 5. Okay, 5 plus 2 is 7 inches. I have that same value to the bottom, 7 inches. Okay, so as I'm finding my moment, MC over I know we can be plus or minus. Our tension and compressive moments are going to be the same. My moment is 3,000, okay, and that was in pound feet. So I need to change it to 12 inches per foot. Okay, C, 7 inches. It doesn't matter whether I'm going up or down. I, 748 inches to the fourth. So I have 3,000, enter, 12 times, 7 times, 748 divided by, and I get that my normal stress is equal to 336.9 psi. So again, that's 3,000 pound-feet that came from here, 500 times 6, 500 enter 6 times, 3,000 pound-feet. I've got to convert it to inches. Okay, so times 12 times 7 inches, that's to the top, divided by 748. and I get 336.9 psi, so we can just call this 337 psi, and that is what we have for our bending stress. And remember, if we wanted to sketch our bending stress, it's going to look, let's see, we have compression on the top, tension on the bottom. It's going to be linear and look something like that. Our shear stress we actually could do because we've already have this cue from putting our fastener on, and we know it's going to come down, then have a big jump because of thickness change, come around, big jump down, and there you have it. So it's just really, this is a matter of learning kind of what these rules are. Oh, so if I wanted to know the force that's being transferred, then when I look at this distribution across my top of my cross section, here's my cross section, and I know that I'm going to go from a stress of 337 psi to 0. So I have this nice triangular stress that's acting in compression on the top, and I know that this has a depth of 2 inches. So I could actually calculate the stress at this point. So if I have 337 enter, the whole thing is 7 inches tall. We can divide that by 7 and get it per inch, multiply it by 5, and I get that the stress at this point right here is 240.714 psi. And I just got that because of the linear relationship that we have in terms of our stress. And now I could find this area of stress. So I have 337 plus 241 divided by 2. That gives my midpoint. And then I have that it is, so that is PSI. That is pounds per inch squared. So now I need to multiply the area that it's acting over so that I can get the actual force that would come through here. So as I'm looking at this, 2 times 7, no, what were, oh, 2 by 4. These were 2 by 4 inches. So if this is pounds per inches squared, I can multiply that by inches squared. That's my area, inches squared. And I can actually get the resultant force that's acting on this top piece. Would be acting on that top piece. So 337 enter, 241 plus 2 divided by is 209, 8 times, and I get the actual force that's acting is 2312 pounds acting over this area. Pounds per square inch times 8. Yep, and there you go.